You ever stop and think about your phone for a second? I mean, how is it streaming music, navigating your route, and handling all your notifications at the very same time without just grinding to a halt? Well, the magic behind all that is something called parallel processing. It's the secret ingredient that really makes all of modern computing possible. So, let's begin our quest for speed. So here's our roadmap for this explainer. We're going to start with why we even need parallelism in the first place. Then, we'll dive into a classic way of sorting these powerful machines into different categories. After that, we'll check out a super clever trick called pipelining, compare the two main blueprints for building parallel computers, and finally, we'll tackle the biggest headache they all share, the memory dilemma.
Okay, so let's start at the very beginning. The real reason we're even talking about this is our endless, insatiable demand for more and more computational power. The old-fashioned way of doing things, one single step at a time, it just can't keep up anymore. Not even close.
At its core, parallel processing is a pretty beautiful and simple idea. Instead of having one lonely processor chugging through a giant to-do list, one item after another, the whole goal is to do lots of those things at the same time. It's a whole family of techniques, really, but they're all designed for one thing: to crank up the computation speed by processing data simultaneously. And get this, parallelism can happen even inside a single processor. Think of it like a little workshop. Instead of one worker trying to do everything, you've got specialists. You've got one unit that just does addition, another that's a pro at multiplication, a third one for logic, and so on. The cool part is they can all be working on different pieces of a problem at the exact same moment.
So we know we want to build these parallel computers, but how do we even start to talk about all the different kinds? Well, way back in 1972, a computer architect named Michael Flynn came up with this really elegant classification system. And believe it or not, we still use it today to make sense of the fundamental blueprints.
Now, to really get Flynn's system, you got to understand two key ideas, which are shown perfectly here. A computer is always juggling two kinds of flows, or streams. You've got the instruction stream. That's the sequence of commands like add this or load that. And then you have the data stream. That's the actual stuff, the numbers and information that those commands work on. Flynn's entire system boils down to one question: how many of each stream can a machine handle at once?
First up is SISD, which stands for Single Instruction, Single Data. This is your classic traditional computer. It processes one instruction at a time, and that instruction acts on one piece of data at a time. It's simple, it's reliable, but it's not parallel.
Okay, now things start getting interesting with SIMD, Single Instruction Multiple Data. Imagine you want to make a photo brighter. The instruction is easy: increase value. But you have to apply that one command to millions of pixels all at once. That's SIMD. A single command gets blasted out to a whole bunch of processing elements, and they all do the exact same thing at the exact same time, but on their own little piece of data.
Then we have MISD, Multiple Instruction Single Data. Now this one is kind of the oddball of the family. You really don't see it much in the real world. Here you have a bunch of processors all running different instructions but on the very same stream of data. Its main use case is in these ultra-reliable, fault-tolerant systems, where you might have several processors all checking each other's work on some critical data feed.
And finally, we get to the big one, MIMD, or Multiple Instruction, Multiple Data. This is what most of us picture when we think of a true parallel computer. You have multiple processors, and each one is basically its own boss, running its own instructions on its own data. They don't have to be in lockstep or anything. From the multi-core chip in your laptop to the world's beefiest supercomputers, most of them fall right into this powerful category.
So Flynn gave us the blueprints, but how do we actually put this parallelism stuff into practice? Well, one of the most powerful and clever techniques is called pipelining. The absolute best way to think about it is like a factory assembly line, but instead of building cars, it's processing computer instructions.
Okay, let's say we need to do this calculation here. A times B plus C, and we need to do it over and over and over again on a long stream of numbers. Normally, a computer would do the entire calculation for the first set of numbers, finish, then start all over again for the second set. Pipelining says, hey, there's a much smarter way to do this.
We just break the whole operation down into separate stages or segments. So the first segment, its only job is to load the numbers A and B. Then the second segment takes those numbers, multiplies them, and also loads C. And finally, the third segment takes that multiplication result and adds C to it. See? Each segment is just one station on our little assembly line.
And this is the big payoff. This illustrates it perfectly. Look at the diagram. Task 1 enters the first segment. On the next tick of the clock, Task 1 moves to segment 2, and a whole new task, Task 2, jumps into segment 1. They're all moving down the line together. But here's the absolutely crucial part. After a few cycles to get the pipe full, a brand new, fully finished result pops out of the end every single clock cycle. The throughput is just incredible.
So how much faster are we talking? Well, in a perfect world, the maximum speedup, which we call S, that you can get from a pipeline is equal to K, which is just the number of segments you have. So a 4-segment pipeline can, at least in theory, get the job done 4 times faster.
Okay, so we've got these cool techniques like pipelining to speed things up. Now let's kind of zoom out a bit and look at the 2 major high-level designs for building parallel machines that use these techniques. We're talking about multiprocessors and multicomputers.
This slide just lays out the core difference beautifully. On one side, you have multiprocessors. These are tightly coupled. The best way to picture this is a team of processors all crowded around a single shared whiteboard. That's their common memory. They communicate by writing things on the board and reading what others wrote. On the other side, you've got multicomputers. These are loosely coupled. This is more like a team where every member has their own private notebook, their own memory, and to communicate, they have to send messages or emails back and forth.
All right, let's focus on those tightly coupled multiprocessors for a second, the ones with the shared whiteboard. This shared memory idea is great, but it also creates a huge central challenge. How in the world do you let all those processors access that memory without them all tripping over each other and creating one massive traffic jam? Well, the simplest approach is what we call the UMA, or Uniform Memory Access Model. Just like the name says, every processor connects to that shared memory in the exact same way. That means it takes any processor the same amount of time to get to any spot in the memory. It's fair, it's easy to program for, but you can probably see the problem. Imagine dozens of processors all trying to use that one connection at the same time. As you add more, that central path becomes a major bottleneck. So, to solve that UMA traffic jam, architects came up with the NUMA model, or Non-Uniform Memory Access. The huge idea here is to physically spread out the shared memory. Each processor gets its own chunk of local memory that it can access super fast. Now, it can still get to the memory attached to other processors. We call that remote memory, but that access is going to be slower because the request has to travel over the network. Now, if you build on that idea of distributed memory, you get to the COMA model, that's Cache-Only Memory Architecture. This is a really fascinating evolution of NUMA. Instead of having a fixed local memory, every single block of distributed memory is treated as part of one giant shared cache. What this does is allow data to automatically move or migrate to the processor that's using it the most, which makes for a really dynamic and efficient system. And finally, let's circle back to our loosely coupled friends, the multicomputers. As you can see here, each node is basically its own self-contained computer with its own processor and its own private memory. There's no shared whiteboard at all. All communication, all coordination, it all happens by explicitly passing messages over a network, just like sending emails. This design is unbelievably scalable, and it's the foundation for many of the biggest supercomputer clusters in the world today.
So from simple little pipelines to these incredibly complex distributed supercomputers, the entire story of modern computing has been this relentless quest for more speed through parallelism. And you know what? That quest is far from over. As our need for computation, for things like AI, big data, and massive scientific simulations continues to just explode, the question on this slide becomes more critical than ever. What new architectures, what new models will power the next big wave of innovation?